Hello, I'm Wei-Che, currently working at Stateful, and we are a team from National Yang University. I'm going to present our work, BLuEMan, a stateful simulation-based fuzzing framework for open-source RTOS Bluetooth low-energy protocol stakes. This is a novel fuzzer designed to uncover vulnerabilities in open-source BLE implementations. According to Bluetooth Market Update report released by the SIG in 2025, Bluetooth shipments in 2024 were approximately 4.9 billion, with over 80% of devices equipped with the BLE protocol. The BLE protocol is often used in low-power short-range transmission scenarios, such as light bulbs and multi-protocol gateway in your home, personal wearable products like smartwatches and wireless headphones, and in-vehicle infotainment systems in your car, and so on. The widespread adoption of Bluetooth low-energy devices has also exposed serious security concerns. Over the years, researchers have identified multiple vulnerabilities in different versions of the Bluetooth protocol stack. Some of these flaws allow attackers to launch denial of the service attacks, while others even enable remote code execution. Well-known examples include BlueBorn, BlueFlag, Frankenstein, Swingstooth, and Bleeding Beach. These cases clearly demonstrate that Bluetooth devices, despite being everywhere in our daily lives, can be exploited by malicious actors if the underlying protocol is not secured. The BLE protocol stack is mainly divided into two parts, the controller and the host. These two components can run on separate processors or on the same processor. The host and controller interact through the host-controller interface, which can use transport such as USB, UART, or other interfaces. The controller is primarily responsible for managing the link layer, performing encryption and decryption, and interacting with the radio hardware. The host, on the other hand, is responsible for establishing connections, pairing and bounding, security management, and executing the BLE application logic. Previous research on Bluetooth fuzzing generally falls into three categories. Type A, emulation-based full-stack fuzzer. It covers the entire Bluetooth stack with QEMU-based host and controller. It runs fast and makes coverage collection easier. But hardware-dependent controller emulation often suffers from low fidelity. Type B, emulation-based host stack fuzzer. It targets the host at the HCI layer. It is faster and coverage-friendly, but lacks the controller, so state completeness is limited and discovered bug may not be remotely triggerable. Type C, hardware-based full-stack fuzzer. It uses real devices to test the full stack with high fidelity. However, it is slow, hard to collect coverage, and usually relies on manual written or auto-generated state machines to craft context-aware packets. After analyzing the advantages and disadvantages of existing designs to achieve speed, state completeness, scalability, high fidelity, and minimal state machine complexity, we developed BLuEMan, a new BLE fuzzing framework. BLuEMan targets to open source BLE applications and BLE protocol implementations. The framework addresses three challenges. First challenge, runtime scalability. Specifically, we have three goals. First, reducing the cost of building test environments so fuzzing does not require purchasing many physical devices. Second, an approach that easily integrates various state-of-the-art coverage tools and sanitizers. And third, a platform that runs much faster than hardware-based solution and is easy to debug. Second challenge, high-quality seed. Existing research shows that meaningful initial seeds are critical to further performance. Therefore, our seeds consist of sequence of context-aware BLE packets, for example, including a complete pairing flow that can actually complete pairing, in order to trigger subsequent protocol behavior, increase testing depth, and raise the chance of finding vulnerabilities. Third challenge, complexity of BLE. Beyond the core specification, there are BLE mesh, multiple profile, and vendor extensions. Consequently, mapping all specifications into state machines makes the system large and hard to maintain. Therefore, our design is focused on an approach that can be easily extended and updated as the BLE protocol evolves, allowing the testing platform to evolve with the BLE ecosystem. To address the first problem, we adopt BabelSim, an open-source physical layer simulator. This simulator can be divided into two parts: simulated devices and shared media. The modem used by simulated devices is emulated by BabelSim. And on top of this modem, we can run the BLE protocol stack. When a BLE application issues a request, it goes through the layers of the protocol stack. And finally, the modem transmits the packets to the shared medium. The shared medium, in turn, can connect to multiple modems, allowing different simulated devices to communicate with each other over the BLE protocol. Since the simulated devices run as ELF executables rather than firmware images, we can directly execute both the fuzzer and the simulated devices on Linux. This allows us to test multiple BLE applications at the same time, without the need for any additional development boards. Only a single Linux host is required. Using BabelSim as a simulation platform also provides a much higher BLE packet transmission speed compared to running BLE applications on development boards or QEMU. And because the applications can be compiled into ELF executables, we can easily apply airfield or other state-of-the-art coverage techniques for instrumentation, collect coverage data, and use it to better guide fuzzing. To address the second problem, we located the packet receiving code in BabelSim's physical layer and inserted our packet interceptor code. Before fuzzing begins, the target application pair is executed once. All packets passing through the interceptor are recorded, and we continue collecting them until the code coverage stops changing. These packets are then organized into packet sequence and used as seeds. For example, in the case of the RTOS profile, we collect a complete context-aware packet sequence that spans multiple protocol layers. This includes the link layer packets that handle low-level communication, the L2CAPE layer that manages logical channels, the ATT layer that provides attribute access, the GATT layer that defines the service framework, and finally, the OTS protocol itself. By capturing the entire sequence across these layers, we ensure that generated test cases accurately reflect real protocol interactions and maintain the dependencies between layers. This context awareness is particularly important for triggering deep logic paths that would be missed if we only consider individual packets in isolation. The surcharge is solved by combining three core components: a packet interceptor, code coverage, and our mutation algorithm. First, the packet interceptor captures real packet sequence with correct context. We reuse those sequences as meaningful seeds. Second, code coverage gives us feedback on program state. It guides the further toward execution paths that have not yet been touched. Because coverage naturally reflects different states as the BLE protocol state evolves, we do not need to build a complex state machine. Finally, we developed a stackable mutation architecture, which is extensible for fuzzing across multiple BLE protocol layers. This approach gives us precise control over where mutations are applied, so we maintain protocol volatility while still maximizing fuzzing effectiveness. Each plugin in the architecture is responsible for a specific protocol layer. It includes a recognition function to detect the presence of that layer in packets, a custom mutation function that can precisely target header or payloads, and a sampling mechanism to decide which layer should be mutated at runtime. By stacking these plugins in sequence, the framework scans flexibility and can easily adapt to different BLE implementations. Most importantly, the modular design allows researchers to extend its support for new or custom protocols. And on top of it, we introduce three additional constraints and adjustments. First, we limit bitwise mutations to link layer, where low-level variation are most effective. Second, we keep upper layer protocol fields, such as L2CAP or ATT, unchanged to avoid breaking higher level semantics. Third, when the payload size changes, we adjust the related length field accordingly so that the packet remains structurally consistent. These constraints and adjustments are carefully designed to preserve packet semantics as much as possible. In doing so, we minimize unnecessary packet rejection by the target, which would otherwise waste execution cycles and reduce the overall effectiveness of fuzzing. Putting these pieces together, we can efficiently explore deep protocol behaviors with context-aware seeds, coverage-guided feedback, and controlled mutations, all without relying on a complex state machine. Now, we will discuss the evaluation of our framework. To select a fuzzing media, we compared the performance of babysyn, root canal, and physical devices. The results show that root canal and physical devices have similar average speeds, but physical devices are highly unstable due to signal interference. In contrast, babysyn runs at approximately 100 times the speed of the other media. And we also compared BLuEMan transmission speed with other studies. It is approximately 162.3 times faster than SwingTooth and about 18 times faster than BT-Fuzz. Notably, BT-Fuzz doesn't perform fuzzing on the controller, but instead sends HCI packets directly to test the host, whereas SwingTooth, like BLuEMan, performs fuzzing by sending BLE packets to the controller. And we also compare our stackable mutation architecture with AFL-only mutator, and observe a coverage improvement of between 6.14 and 256.49%. It is important to point out that for the BLE mesh benchmark, most packets are encrypted, and these mutators weren't tuned for encrypted payloads. As a result, the three methods showed only small differences, and all achieved relative low code coverage on this example. We compare BLuEMan to the state-of-the-art BLueTools. Following BLueTools' instruction, we flash its firmware on an ESP rover kit, which is the left device in the lower right figure. The testing target of BLueTools ran the host on Linux and used a NRF 2840 development kit as a controller. BLuEMan achieved approximately 1.55 times to 1.69 times higher code coverage than BLueTools. Although each experiment was run for 5 hours, BLueTools coverage growth stopped increasing after roughly 40 seconds, so the figure shows only the first 40 seconds. To summarize, we present BLuEMan, a simulation-based fuzzing framework for BLE protocol stakes, but by combining an RTOS with a physical simulator, BLuEMan provides an efficient, high-fidelity, and scalable platform for BLE fuzzing. One of the key features of BLuEMan is its novel man-in-the-middle architecture, which enables automated seed collection coupled with packet-driven workflow. This design significantly streamlines state management during fuzzing. Using BLuEMan, we were able to uncover 4 new vulnerabilities spanning different layers of the BLE stack, demonstrating the framework's effectiveness in identifying security issues across the layers. Thank you for your attention. On this slide, we have included QR codes that take you directly to our GitHub repository, and Zenodo snapshot that archives the exact source code used in this work, and of course, the full paper for further details. These resources are open and available for you. Please feel free to check them out if you were interested. And of course, don't hesitate to reach out to us if you have any questions or thoughts you'd like to discuss.